So here three complex numbers z1, z2 and z3 whose mod z1 is 2, mod of z2 is 3, mod of z3 is 4 and mod of 2 times z1 plus 3 times z2 plus 4 times z3 is equal to 4. Then the value of 8 times z2 z3 plus 27 times z3 z1 plus 64 times z1 z2 mod is equal to. Let's consider 8 times z2 z3 plus 27 times z3 z1 plus 64 times z1 z2 mod, and here let us consider or multiply and divide with z1 z2 z3, and here 27 times z3 z1 divided by mod of z1 z2 z3, and again here 64 times of z1 z2 divided by z1 z2 and z3 in the mod. So we can write mod of z1 z2 z3 into mod of 8 upon z1 plus 27 upon z2 plus 64 upon z3, and since we know that mod of z1 z2 is equal to mod z1 into mod z2, so by using this property I separated, and also we can write mod of z1 into mod of z2 mod of z3 into, and we know that reciprocal of a complex number, that is 1 upon z, is equal to z bar divided by mod z square. Since we know that z into z bar is equal to mod z square, so from here we can write 1 upon z is z bar upon mod z square. So 1 upon 8 upon z1 we can write 8 into z bar divided by mod z1 square z1 bar divided by mod z1 square, and again plus 27 times of 1 upon z2 can be taken as z2 bar divided by mod z2 whole square, and again plus 64 times mod z3 bar divided by mod z3 square. z1 value is 2 and z2 value is 3 and z3 value is 4 into 8 times z1 bar divided by mod z1 square is divided with 4, and 27 times z2 bar divided with z2 square is 9, and again here 64 times of z3 bar divided by mod z3 square is 16. So which can be taken as 2 3s are 6, 6 4s are 24 times. Here it is 2 times of z1 bar, and here 3 times of z2 bar, plus here 16 4 times of z3 bar, which can also be taken as so 24 times of 2 times of z1 plus 3 times of z2 plus 4 times of z3 whole bar. And let's see, since we know that z1 plus z2 z1 bar plus z2 bar can be taken as z1 plus z2 whole bar, so we can write here 2 and 24 times 2 times z1, 3 times z2, 4 times z3 whole bar can be taken, and also we know that mod of z bar is equal to mod z, so which can be taken 24 times 2z1 plus 3z times z2 plus 4 times z3 complex number mod is same as its conjugate, and it's given to us mod of 2z1 plus 3z2 plus 4z3 is 4, so we can write 24 into 4, which is 96. So 96 is the answer, which is option D. Roots of the equation x square plus bx minus c is equal to 0, where b and c are positive. And we know that for quadratic equation ax square plus bx plus c is equal to 0, if alpha and beta are the roots, we can consider sum of the roots is equal to minus b by a and product of the roots is equal to c by a. Let us assume here alpha beta are the roots of x square plus bx minus c is equal to 0, and then product of the roots is equal to minus c upon 1, and c is positive, so negative c will be negative, so we can say alpha beta is negative, and product of two numbers is negative, which implies that alpha both must be of different sign. If alpha is positive, so plus into minus is negative and minus into plus is negative. If both are positive is positive, both are negative is positive, so in this case we can consider both the roots are, we can conclude that both the roots are of opposite sign. Both cannot be different same sign, so we can go with an option C. If f of z is equal to 7 minus z upon 1 minus z square, where z is a complex number 1 plus 2i, then mod of f of z is equal to, if z is equal to a plus ib, then we have mod z is equal to root of a square plus b square, and also if two different complex numbers are there, z1 upon z2, the mod we can write it as mod z1 by mod z2. So let us simplify here. F of z is equal to 7 minus z upon 1 minus z square. So that is 7 minus, we can substitute z is equal to 1 plus 2i divided by 1 minus 1 plus 2i whole square. So we can simplify 7 minus 1 minus 2i divided by 1 minus of a plus b whole square is a square plus b square plus 2ab. That is 7 minus 1 6, 6 minus 2i upon 1 negative 1 0, and again here 4 I square is negative 1, so minus of minus plus 4, and again here minus 4i. Now consider mod of f of z, which is equal to mod of 6 minus 2i divided by 4 minus 4i. This can also be written mod of 6 minus 2i divided by mod of 4 minus 4i, or we can take 2 common, 2 times mod 3 minus I divided by, and here denominator 4 can be taken, 4 times mod of 1 minus I. So that is 1 upon 2 times of, since we know that mod z is equal to root of a square plus b square, so we can write 3 square 9 plus minus 1 whole square divided with again here 1 square plus negative 1 whole square. So 1 by 2 into root of 9 plus 1, that is 10, divided by root of 2. So we can write root 2 into root 5 divided by 2 into root 2. So we can say root 5 upon 2. And also mod z can be taken as under root of 1 plus 2 square, 1 square plus 2 square, which is equal to root 5. So root 5 is mod z, so we can simplify. This is mod z divided by 2. So we can go with an option A, mod z upon 2. If alpha and beta are the roots of the equation x square plus px plus 3p upon 4 is equal to 0, such that mod of alpha minus beta is equal to 10, then p belongs to the set. And let's recall, for a quadratic equation ax square plus bx plus c is equal to 0, if alpha and beta are the roots, then we have sum of the roots alpha plus beta is equal to minus b by a, and product of the roots is equal to c by a. And we can also write alpha minus beta whole square is equal to alpha plus beta whole square minus 4 alpha beta. We can use this identity. So that let us consider mod of alpha minus beta is equal to root 10, and also here for the equation x square plus px plus 3p upon 4 is equal to 0, sum of the roots can be taken as minus p upon 1, that is negative p, and product of the roots can be taken as c upon a, that is 3p by 4. So squaring on both sides here, so we have alpha minus beta whole square is equal to 10. So alpha minus beta whole square, we can write it as alpha plus beta whole square minus 4 times of alpha beta is equal to 10. And alpha plus beta is minus p, so we can write negative p whole square minus 4 times of alpha beta is 3p upon 4 is equal to 10. So we can write p square minus 4 upon 4 gets cancelled, so p square minus 3p minus 10 is equal to 0. So let us simplify this quadratic equation. So p square minus, we can write this as 5p plus 2p minus 10 is equal to 0. So factorization, p into p minus 5 plus 2 times of again p minus 5 is equal to 0. So p plus 2 into p minus 5 is equal to 0. So p value can be negative 2 or p value can be 5. So therefore p belongs to the set, we can say minus 2 and 5. So minus 2 comma 5, which is option C. If the amplitude of z minus 2 minus 3i is pi by 4, then the locus of z x plus iy is. And we know that if z is equal to a plus ib, a complex number, and if theta is the amplitude of the complex number z, then we have tan theta is equal to b upon a. So here, let z1 is equal to the complex number z minus 2 minus 3i. For z is equal to x plus iy, so we can write x plus iy minus 2 minus 3i. We can write x minus 2 plus I times of y minus 3. So which is in the form of a plus ib. Then its amplitude of z1 is equal to pi by 4, that is tan pi by 4 is equal to b upon a, that is y minus 3 upon x minus 2. So tan pi by 4 value is 1. 1 is equal to y minus 3 upon x minus 2. So cross multiplying, you'll get x minus 2 is equal to y minus 3, or x minus y minus 2 plus 3 is equal to 0, or we can write x minus y plus 1 is equal to 0. So which is option D. So the locus of z is equal to x plus y can be taken as x minus y plus 1 is equal to 0. Here given two complex numbers, z1 is equal to root 3 plus I root 3 and z2 is equal to root 3 plus I, and we need to check whether this complex number z1 upon z2 whole power 50 lies in the which quadrant. So consider z1 by z2. So we can write root 3 plus I root 3 divided by root 3 plus I. Root 3 taken common, 1 plus I upon root 3 plus I. Let's consider its square. So root 3 whole square 3 times of 1 plus I whole square divided by root 3 plus I whole square. Let's do separately here. 1 plus I whole square is equal to 1 square plus I square plus 2 into 1 into I, which is 1 minus 1 plus 2I. So that is 2I. Similarly, root 3 plus I whole square is equal to root 3 whole square plus I square plus 2 root 3 I. That is 3 minus 1 plus 2 root 3 I. That is 2 times of 1 plus root 3 I. So we can write here z1 by z2 whole square is equal to 3 times of 2i divided by 2 times of 1 plus root 3i. So which can also be written 3i divided by 1 plus root 3i. And we also know that cube roots of unity 1 omega square for the equation 1 plus x square is equal to 0, where omega square is equal to minus 1 minus root 3i divided by 2. So here we can write 2 omega square is equal to minus 1 minus root 3i, or minus 2 omega square is equal to 1 plus root 3i. So instead of writing 1 plus root 3i, we can also write minus 2 omega square. So I can write here 3 times of I divided by minus 2 omega square. This is z1 by z2 whole square. Now let us consider z1 by z2 whole power 50, that is whole power 25. So z1 by z2 whole square whole to the power 25, which comes 50, which is equal to 3i divided by minus 2 omega square whole power 50, that is 3 power 50 into I to the power of 50 divided by minus 2 to the power 50 into omega to the power 100. And now here I to the power 50, so we can write I to the power of 4 times of 12 plus 2. When 50 is divided with 4, the remainder is 2. So we can consider as I square, which is equal to minus 1, since we know that I to the power 4n is equal to 1. Or I to the power of 4n plus 2 can be taken as I square, which is equal to minus 1. And similarly omega to the power 100, since omega cube is equal to 1, omega power 100 is equal to 100 is divided with 3, so 3 into 33 plus 1, so the remainder is 1. So we can consider omega power 100 is omega power 1, that is omega. So let us write here 3 power 50 divided by minus 2 power 50, we can write 2 power 50 since power is even, into I to the power of 50 is I square, that is minus 1, divided by omega power 100 is omega, and minus 1 upon omega. Or from here we can say 1 upon omega is equal to omega square, or minus 1 upon omega is equal to minus omega square. So here we can write 3 by 2 whole to the power 50 into minus omega square, and we know that omega square is equal to minus 1 minus root 3i divided by 2, then negative omega square is equal to plus 1 plus root 3i divided by 2. So we can write 3 upon 2 whole power 50 into 1 plus root 3i divided by 2, or we can write 3 by 2 whole power 50 times 1 upon 2 plus root 3 by 2 to the power I. So here we can see that the real part and imaginary part both are positive. 1 by 2 is positive, root 3 by 2 is also positive. So we can consider 3 by 2 whole power 50 is also positive. So we can say that this complex number which lies in the first quadrant. When x coordinate, y coordinate both are positive, a complex number will be lying in the first quadrant. So we can go with an option A, first quadrant. If a comma b are the roots of the equation x square minus 2x minus 1 is equal to 0, then what is the value of a square into b power minus 2 plus a power minus 2 into b square? We know that for the quadratic equation ax square plus bx plus c equals to 0 if alpha and beta are the roots. So we can say alpha plus beta is equal to minus b upon a, and product of the roots alpha beta is equal to c upon a. So here a and b are the roots. Since a and b are the roots, so we can write sum of the roots is equal to minus of minus 2 divided by 1, which is 2, and product of the roots ab is equal to minus 1. And now we need to find a square into b to the power of minus 2 plus a to the power minus 2 into b square. That is a square by b square plus b square by a square, which is a power 4 plus b power 4 divided by a square b square. And also here alpha square plus beta square is equal to alpha plus beta whole square minus 2 alpha beta, we can remember. So similarly a power 4 plus b power 4 we can write a square whole square plus b square whole square divided by ab whole square we can write. So which can also be written a square plus b square whole square minus 2 a square b square. So a square plus b square we can also write it as a plus b whole square minus 2ab, this is the whole square, and again minus 2 times of ab whole square divided by ab whole square. So let us substitute a plus b value is 2, so 2 square minus 2 times of ab value is minus 1, this is whole square minus 2 times of minus 1 whole square divided by ab value minus 1 whole square. So which is equal to 2 to the 4 minus of minus plus 2 whole square minus 2 times of 1 divided by 1, which is equal to 4 plus 2 6 square is 36. 36 minus 2 divided by 1, that is 34. So 34 is the answer, which is option D. If a comma b and c are real numbers, then roots of the equation x minus a into x minus b plus x minus b into x minus c plus x minus c into x minus a is equal to 0 are always. So after simplifying, we'll get x square minus of a plus b of x plus ab, and here we can get x square minus of b plus c of x plus bc, and here x square minus of c plus a of x plus ac is equal to 0. So 1x square, 2x square and 3x square here, and minus of x coefficients are a plus b plus c and c plus a, that is 2 times of, okay, right, 2 times of a plus b plus c of x, and the constant terms are ab plus bc plus ac, ab plus bc plus ca, which is equal to 0. And since the roots are abc are real numbers, the roots of the equation, to check whether they are real imaginary, let us find the discriminant. Discriminant set d is equal to b square minus 4ac. For the quadratic equation ax square plus bx plus c. So here b square is, let me change. So here we can write minus 2 times of a plus b plus c whole square minus 4 times of 3 into ab plus bc plus ca. This is discriminant value d. So which is equal to 4 times of a plus b plus c whole square minus, or 4 can be taken common, 3 times of ab plus bc plus ca, which is equal to 4 times of a plus b plus c whole square, we can write a square plus b square plus c square plus 2ab plus 2bc plus 2ca minus 3 times of AB minus 3 times of BC minus 3 times of CA, which is equal to 4 times of A square plus B square plus C square minus AB minus BC minus CA. And we know that the value of A square plus B square plus C square minus AB minus BC minus CA is half of A minus B whole square plus B minus C whole square plus C minus A whole square. Let us see that. Consider A square plus B square plus C square minus AB minus BC and minus CA. Let us multiply and divide with 2. So we'll get 2A square plus 2B square plus 2C square minus 2AB minus 2BC minus 2CA, which is equal to 1 by 2 times. We can write A square plus B square minus AB, 2AB we can write, and again B square plus C square minus 2BC we can write, and again C square plus A square minus 2CA we can write. So that A square plus B here A square plus A square 2 times A square, B square plus B square 2 times B square, and C square plus C square is 2 times C square, and minus 2AB minus 2BC minus 2CA. So we can write 1 by 2 times. So this is A minus B whole square, and here it is B minus C whole square, and here it is C minus A whole square. So we can say that A square plus B square plus C square minus AB minus BC minus CA is half of A minus B whole square plus B minus C whole square plus C minus A whole square. Hence discriminant D is equal to, so 4 times of A square plus B square plus C square minus AB minus BC minus CA, we can write it as 4 into 1 by 2 times of A minus B whole square plus B minus C whole square plus C minus A whole square, and that is 2 times of A minus B whole square plus B minus C whole square plus C minus A whole square. And here we can consider A minus B whole square, B minus C whole square, and C minus A whole square all are positive. So either they can be A, B, C are equal, or it can be equals to A minus B whole square is greater than or equals to 0, B minus C whole square greater than or equals to 0, C minus A whole square is always greater than or equals to 0. So we can consider this is greater than or equals to 0. So the discriminant is greater than or equals to 0. We can say that the roots of quadratic equation are real. So we can consider that they are always real, which is option A. Here in this problem, we need to identify among the roots of the equation 2 times of 1 plus a of x square minus 4 times of 2 minus a of x minus 5 minus 3 is equal to 0, having the greater modulus. So for that we need to find the roots of this equation. Since for the equation ax square plus bx plus c equals to 0, we can identify the roots by using the formula x is equal to minus b plus or minus under root of b square minus 4ac divided by 2a. So when comparing with this, a is equal to 2 times of 1 plus I, and b is equal to negative 4 times of 2 minus I, and c is equal to negative 5 negative 3I. Let's find first b square minus 4ac, which is equal to minus 4 times of 2 minus I whole square minus 4 into 2 times of 1 plus I into c value is negative 5 negative 3I. So we can write negative 4 whole square, that is 16 times of 2 minus a whole square, and again here 4 2s are 8, and again negative negative positive, so 8 times of 1 plus I into 5 plus 3I. So we can write 16 times of 4, and I square is minus 1 minus 4I, and again here 8 times, or we can take 8 times of, let us multiply 5 plus 5I plus 3I minus 3. I square is minus 1. So 16 times of 4 minus 1, 3 minus 4i plus 8 times of here 2 plus 8i. So here 16 times of 3 minus 4i, and here also 16 we can take common, 1 plus 8 2s are 16, so 4i. So 16 is totally taken common. So 3 minus 4i plus 1 minus 1 plus 4i. Some on simplification will get 16 times of 3 plus 1 4. That's all, 16 into 4. So you'll be getting 16 fours are 64. So we get the roots. X is equal to minus b, that is minus of minus 4 times of 2 minus I, plus or minus under root of b square minus 4ac is 64 divided by 2 times of 2 into 1 plus I, 2a. So which is equal to 4 times of 2 minus I plus or minus 8 upon 4 times of 1 plus I, that is 4 taken common, 2 minus I plus or minus 2 divided by 4 times of 1 plus I. So we get here two roots, that is 2 minus I plus 2 upon 1 plus I, or we can say 2 minus I minus 2 upon 1 plus I. So we get the roots. Let us consider z1 is equal to, so 2 plus 2 4 minus I divided by 1 plus I, or the second root z2 is equal to minus I divided by 1 plus I. Let's simplify this. Z1 is equal to 4 minus I. Let's multiply with 1 minus I in the numerator and denominator. So we get 4 ones are 4 minus I minus 4I, and again here plus I square is minus 1 divided by 1 plus I into 1 minus I is 1 square 1 minus I square is minus 1, so 1 plus 1. So Z1 is equal to 3 minus 5I divided by 2. And similarly Z2, multiplying and dividing with 1 minus I, so we'll get negative I times of 1 minus I divided by 1 plus I into 1 minus I is 2. So we can write minus I. So here minus I into minus I plus I square. So minus 1 minus I divided by 2. Now let's identify mod. Mod Z1 is equal to 1 by 2 times of mod of 3 minus 5I, which is equal to 1 by 2 root of 3 square plus minus 5 whole square, that is 1 by 2 times root of 9 plus 25, which is 1 by 2 root 34. Similarly, mod z2 is equal to 1 by 2 times of root of minus 1 whole square plus minus I minus 1 whole square, which is 1 by 2 into root 2. So root 2 and root 34 is greater than root 2. So we can consider that mod of z1 is greater than mod of z2. So among the two roots, z1, that is 3 minus 5 upon 2, is the root which is having the greater modulus. So we can go with an option A. We need to find the roots of the equation. X power 4 minus 2x power 3 plus x is equal to 380. Let's verify among the options. So two real numbers, say 5 and minus 5, 4 and minus 4. Let's check with 5. So 5 power 4, 625 minus 2 times of 5 cube is 125 plus 5 is equal to 380. So that is 625 minus 250 plus 5, 625 plus 5, 630, 630 minus 250 is 380. So we can say that x is equal to 5 is the root. And now coming to the 4 or minus 4, let's check with 4. So you're getting 4 power 4, it is 64 minus 4 cube is, sorry, 4 power 4 is 256. 4 power 4 minus 2 into 4 power 3 plus 4. We need to check whether it is 380 or not. So 4 square is 16, 16 is 256 minus 64 2 is 128 plus 4. So 256 plus 260 minus 128 cannot be equal to 380. So we can say this 4 is not a root. So let us check with the minus 4. So minus 4 whole to the power 4. So minus 2 times of minus 4 whole power 3 plus minus 4 is equal to 380. We have to check. So that is 256, and here it comes plus 128 and again minus 4. So we'll be getting 256 minus 4 is 252 plus 128 is 380. So we can just confirm that minus 4 is a root. So x is equal to 5, x is equal to 5 and x is equal to minus 4. These are the two roots we are getting. So among the four options, like we can say that only option A is having 5 and minus 4 at the roots, but anyhow we will find the other roots. The given equation, we can write x to the power 4 minus 2x power 3 plus 0x square and plus x minus 380 is equal to 0. Let us use the remainder theorem. Since we got the roots 5 and minus 4, so first I will take 5. So coefficients are here 1, minus 2, 0, 1 and minus 380. Then you will get 0, start with 0, 5 into 0, 1 plus 0 is 1, 5 ones are 5, and again minus 2 plus 5 is 3, 5 into 3 is 15, 0 plus 15 is 15, and 15 5s are it is 75. So 75 plus 1 is 76, 76 5 times you will be getting 380, so remainder is the 0. So we can say x is equal to 5 is a root. And coming to the next one, since also we have x is equal to negative 4, let's consider negative 4. Start with 0, 1 plus 0 is 1, minus 4 into 1 is negative 4, 3 minus 4 is negative 1, so minus 4 into minus 1 is 4, and 15 plus 4 it is 19, so 14 nines are 76, so we'll get minus 76, so we'll be getting again 76 minus 76 is 0, so the remainder is 0. So at last, after getting two roots, the third equation, second degree equation is, so we can write x minus 5 into x plus 4 into, here coefficient of x square is 1 and coefficient of x is negative 1 and the constant is plus 19 is equal to 0. So let us find the roots for this equation by taking the formula minus b plus or minus under root of b square minus 4 into 1 into 19 divided by 2a. So you'll get x is equal to 1 plus or minus under root of 1 minus 19 fours are, so 76. So we can write divided by 2 into, so 2 into 1 here. So x is equal to 1 plus or minus root of minus 75. So we can write 25 threes are, so 5 root 3 I we can write divided by 2. So minus 1 or plus 1 plus or minus 5 root 3 I divided by 2, or we can also write x is equal to 1 plus or minus 5 times of root minus 3 divided by 2. Instead of writing I, we can write minus 3. So among these four, the first option is what we expected. So the other two roots are also 1 plus or minus 5 root of minus 3 divided by 2. So we can conclude the option A.